let's take a look at thin film interference. Thin film is a little bit of oil on water, or a soap bubble, or some sort of anti-reflective coating on optical instruments to diminish or amplify reflection. And with oil on water and soap bubble, you're familiar with, and you remember that if you're looking at them, you sometimes see a little bit of a rainbow coloring on it. So this is what we're talking about when we're saying thin film interference. There is some sort of interference of light where some colors appear brighter, some disappear completely. So there are two things to consider when we're looking at this. The first thing is the reflection of the top and bottom of a thin film, and the second is the path length difference based on the thin film thickness. So both of these contribute to the thin film interference, and we can manipulate something here so that we can work it out to our advantage. Let's say that we want to build an anti-reflective coating and we need to know what the thickness should be of the thin film so that we get anti-reflective rather than reflective coating. So let's start by looking at the first thing. Here I have, so I'm considering the reflection of the top and bottom of a thin film. So in my drawing I have a medium 1, so that's everything on top of here. Then I have the thin film that I'm talking about, and the thin film is like really thin, but in order for us to see anything I have to make it thick. And then that thin film is sitting on top of a medium 3. So here we have 3 different media, and the 3 of them have different indices of refraction. So I'm going to have the index of refraction of the medium in which the light starts, then I have the index of refraction of the thin film, and the index of refraction of the material that the thin film is sitting on. We're starting out with a beam coming in, a beam of light coming in from the first medium. Now we know that the beam of light will reflect based on the law of reflection, where the incident angle equals the reflected angle, the angle of reflection I should say. Then that beam also refracts, and it refracts obeying Snell's law. So we have a beam starting out, it reflects and it refracts. Now this beam inside the thin film is going to hit another interface between itself and medium 3. So it will reflect again and it will refract. So this reflected beam then is going to reflect and refract, and then that will reflect back and forth in here and refract. So we're going to have a whole bunch of different beams of light coming out of here. But what we're interested in is first order, basically the reflection off the top and off the bottom of the thin film. So we're just looking at reflections 1 and 2. Note that this beam is reflected and then it's refracted. It turns out that the refraction has no contribution to this interference bit, so that's why I'm going to call this beam also reflected from the bottom surface of the thin film. So what we have to consider here is the index of refraction of the media, and in my table I'm going to explain exactly what is significant here about the indices of refraction. So here I'm saying if the reflection is off of a lower n, off a lower index of refraction, there is no phase shift and there is no path length difference. So I guess let's backtrack and see what exactly we're talking about when I'm mentioning phase shift and path length difference. So remember that if I draw a sine wave and let's have a y-axis here for all of them. So here is a sine wave like that, and here is a sine wave that looks pretty much the same, and here's another sine wave. So we have 3 sine waves, and we have to interpret things about them. What is important to know is what the x-axis is. So the top one may be time, the middle one may be radians or an angle, degrees, and the bottom one could be a length, x. So remember that if my x-axis is time, then the distance from one peak to the next, so that's where the pattern starts repeating itself, that distance is going to be one period. If I look at the same thing for angles, I know that this would be 360 degrees, or in radians, 2 pi radians. In the bottom picture, if I go from here to there, the length of one pattern is called the wavelength. So this is 1 lambda for the wavelength. So then back in the table here, I'm talking about a phase shift of 0 and a path length difference of 0. That's pretty obvious. But then when I have a phase shift of pi, that corresponds to a path length difference of lambda over 2. So what is pi? Well, pi would be from here to there. And if I extend that to the next graph, I see that the pi, this much, corresponds to half a wavelength, that much. Okay, so that's where this all comes from. Now, back to thin film interference. So when a beam of light reflects off an index of refraction that is lower than the previous one, that it started in, then there is no phase shift, there is no path length difference. But if it reflects off of a higher index of refraction, so let's say that N2 was 1.5 and N1 was 1. So we're going from 1 to 1.5, then that reflection is going to pick up a phase shift or a path length difference of half a wavelength. So that is what we're interested in when we are considering the reflection. Do we have no path length difference, or do we have a lambda over 2 path length difference? Or if we're looking at angles, phase shifts, no phase shift or pi phase shift. Those are the kinds of things we're going to be looking at. And I'm going to discuss this more a little bit later, but let's look at part 2 of what is important to consider here. So how do we take the path length difference into account? So I have a very carefully drawn thing here. It was not easy to do. So I start out with a beam of light, and it wiggles like this. It's a wave, right? Then when it passes into a different medium, the wiggles are going to change. And they're staying the same. They have the same path. They have the same wavelength in the medium, but there's going to be the same wavelength in here. And the reason for that is because wavelength in a medium is going to be the wavelength in vacuum divided by the index of refraction of the medium. So an important thing to remember is that the frequency of light when it passes from one medium to another does not change, but the wavelength does. And since frequency doesn't change, but wavelength does, multiplying frequency by wavelength, the speed of light changes when it passes from one medium to the other. Okay? So what I drew here is the different wavelengths of light in this medium versus the wavelength of light in this medium. Now, this is the incident beam that we have here. That is the reflected beam that goes down, and this is the reflected beam that comes back up, and then there is reflection that corresponds to that. What I didn't draw here, and I guess I'll give it a try, is the reflected beam up here. So that reflected beam would correspond to this reflected beam. So you'll notice that the beam reflected from the bottom here, so we're comparing these two guys, this beam picked up more path length in its travel. So this one only went this much, the other one went more, and based on the fact that it goes in the medium twice, we'll say that there is a path length difference between this beam and that beam. The other thing that we have to point out here is that usually in problems and in real life, we're going to consider that light will strike, this medium almost perpendicularly. So it's going to go perpendicular, it goes through, comes back, and comes back out. But it's hard to visualize that when everything is overlapping. So I draw this at an angle to show you that this part is going to be going down through the thin film, coming back up through the thin film. And if we're saying that that the light beam goes perpendicular, then the path length difference is about 2L, twice the thickness of the thin film. It goes down 1L, comes back up 1L, because we're looking at it going down through it and back up. So there are two equations for which we can adjust the thickness, and the two equations are this. We have one that says 2L, the path length difference between the two beams, is going to be m lambda in the medium, lambda in vacuum divided by index of refraction of the medium, or 2L is m plus 1/2 lambda in vacuum divided by index of refraction of the medium. So what are we doing here? Well, we're basically keeping whatever reflection we had based on just a reflection, whatever phase difference we had or whatever path length difference we had based on just a reflection, and we're keeping that. In this situation, we're actually adding half a wavelength so that this beam will be switched to whatever it was when it bounced off of there. So this beam can become lambda over 2. It would have an extra lambda over 2 path length difference, or it can be phase shifted by pi radians based on the fact that it goes through the medium. We pick up another half a wavelength, and then it gets reflected here, and then we compare whether these two beams are in phase or out of phase. So let's take a concrete example. Let's say that N1 is 1, N2 is 1.3, and N3 is 1.5. So first thing we're doing is following the reflection. So we have this beam coming in, it reflects off the top, but it goes from a medium with index of refraction N1, which is 1, to one that is 1.3. So it's reflection of a higher index of refraction because 1.3 is higher than 1. So then it picks up a wavelength, a path length difference of lambda over 2. Then the second beam, now we're only looking at the reflection. So at the bottom of the thin film, the second beam is going to be reflected off of 1.5. So it starts in 1.3 and it goes up to 1.5. So again, we're reflecting off a higher index of refraction, so we're picking up half a wavelength. So I'm going to write up here that this beam is also half a wavelength different. It has a path length difference of half a wavelength or a phase shift of pi. So now we're going to compare these two beams, and we know that each one of them has a path length difference of lambda over 2 with respect to the original beam, but with respect to one another, they are not phase shifted. They both were phase shifted by lambda over 2, which puts the two of them in phase. In phase means that they would have constructive interference, so there would be a reflection visible. Now, once we take care of the phase, the path length difference, when we determine whether they are in phase or out of phase with respect to one another based on reflection, we're going to check to see what the problem is asking us. Let's say that the problem says, what should be the thickness, L, of the thin film so that the reflected light is not visible. So right now, due to just reflection, my light is going to be visible because this and that are in phase with one another. But if the question asks us to figure out the thickness here, the L, so that the light is not visible, then we have to pick up another half a wavelength. And to do that, we're going to use this equation. So we're changing whatever happened here due to reflection by adding half a wavelength and bringing this beam by half a wavelength out of phase, or pi radians out of phase. Now, let's say that the problem said, okay, what is the thickness of the film so that these two beams are going to be in phase with one another, so the light is going to be reflected? Well, they are already reflected. So we're going to use this equation where we keep that reflection rather than change it by using this equation. Okay? Another example, so let me erase this. Let's say that we have an index of refraction 1 here, 1 point, that's not a 1, 1.5 there, and 1.2 in the third medium. So we start out with the reflection bit. So this original beam is going to strike the top of the thin film and it will be reflected. But it goes from 1 to 1.5. 1.5 is larger than 1, so we have a lambda over 2 path length difference. Then this beam is going to be refracted and it gets reflected from the bottom of the thin film, but it gets reflected from 1.2. So it had been in 1.5 and now it's reflected off of a lower index of refraction. There is no path length difference. So this will be 0. So we're done with the path length difference based on just a reflection off the top and bottom of the thin film. We compare these two and it looks like they are out of phase, so they will destruct. If the problem asks us to find the thickness of the thin film for constructive interference, so if we want to actually see the reflected light, since these two are out of phase, we have to change that to in phase by adding half a wavelength. So this equation changes from destructive to constructive. But if the problem had asked us to keep it as destructive, we would have used this equation and the solve for the thickness, and the beam that was the beams that were reflected off the top and bottom of the thin film would have been interfering destructively.